Hey Charles, how's it going?
It's going pretty well, Michael. How are things going with you?
Good. You know, I'm excited to tell you about neural networks today. You may be familiar with neural networks because you have one in your head.
I do?
Well, yeah, I mean, you have a network of neurons, like you know neurons, like brain cells. I'll draw you one.
Okay.
So this is my attempt at drawing a nerve cell, a neuron, and you've got billions and billions of these inside your head, and they have, most of them have a pretty similar structure. That there's the kind of the main part of the cell called the cell body, and then there's this thing called an axon, which kind of is like a wire going forward to a set of synapses, which are kind of little gaps between this neuron and some other neuron. And what happens is information, spike trains, woo-woo, travel down the axon. When the cell body fires, it has an electrical impulse. It travels down the axon and then causes, across these synapses, excitation to occur on other neurons, which themselves can fire, again, by setting out spike trains. And so they're very much a kind of a computational unit, and they're very, very complicated. To a first approximation, as is often true of first approximations, they're very simple, sort of by definition of first approximation. So in the field of artificial neural networks, we have kind of a cartoonish version of the neuron and networks of neurons, and we actually put them together to compute various things. And one of the nice things about the way that they're set up is that they can be tuned or changed so that they fire under different conditions and therefore compute different things. And they can be trained through a learning process. So that's what we're going to talk through if you haven't heard about this before.
Okay.
So we can replace this sort of detailed version of a neuron with a very abstracted away kind of notion of a neuron. And here's how it's going to work. Is we're going to have inputs that are kind of, think of them as firing rates or the strength of inputs, x1, x2, x3 in this case. Those are multiplied by weights, W1, W2, W3, correspondingly. And so the weights kind of turn up the gain or the sensitivity of the neuron, this unit, to each of the inputs respectively. Then what we're going to do is we're going to sum them up. So we're going to sum over all the inputs the strength of the input times the weight. And that's going to be the activation. Then we're going to ask, is that greater than or equal to the firing threshold? And if it is, then we're going to say the output is 1. And if it's not, we're going to say the output is 0. So this is a particular kind of neural net unit called perceptron, which is a very sexy name because they had very sexy names in the 50s.
They did.
When this was first developed. All right. So this whole neuron concept gets boiled down to something much simpler, which is just a linear sum followed by a thresholding operation. All right. So it's worth kind of thinking, what sort of things can networks of these kinds of units compute? So let's see if we can figure some of those things out. All right, just to make sure that you understand, let's think through an example. Let's imagine that we've got a neuron, we've got one of these perceptron units, and the input to it is 1, 0, negative 1.5 for the three different inputs in this case, and the corresponding weights are a half, 3/5, and 1. And the threshold, let's say, is 0, meaning that it should fire if the weighted sum is above 0 or equal to 0, and otherwise it should not fire. So what I'd like you to compute is, based on these numbers, what the output y would be in this case. All right, Charles, you want to help us kind of work through this example?
Sure. So we multiply x1 times w1, so that gives us a half.
Mm-hmm.
We multiply 0 times 3/5,
Mm-hmm.
which will give us 0.
Mm-hmm.
And we multiply minus 1.5 times 1, which will give us minus 3/2. And so the answer is negative, whatever it is.
It is, right. So this was negative 1.5 plus a half, so it should be negative 1.
Right.
But that's not the output that we should actually produce, right? That's the activation. Right. What do we do with the activation?
Well, we see if the activation is above our threshold theta, which in this case is 0, and it is not. So the output should be 0.
Good. All right, well, we'd like to try to get an understanding of how powerful one of these perceptron units are. So what is it that they actually do? So they they return, in this case, either 0 or 1 as a function of a bunch of inputs. So let's just, for simplicity of visualization, let's just imagine that we've got two inputs, x1 and x2. So Charles, how could we represent the region in this input space that is going to get an output of 0 versus the region that's going to get an output of 1?
What are the weights?
Right, so indeed the weights matter. So let's give some concrete values to these weights. And let's just say, just making these up, that weight 1 is a half, weight 2 is a half, and our threshold theta is 3/4. So now what we want to do is, again, break up this space into where is it going to return 1 and where is it going to return 0.
Okay, so I think I know how to figure this out. So there's kind of there are two sort of extreme examples. So let's take a case where x1 is 0.
x1 is 0. Okay, good. So that's this y-axis.
Right. So if x1 is 0, what value would x2 have to be in order to break a threshold of 3/4? Well, the weight on x2 is a half. So then the value of x2 would have to be twice as much as the threshold, which in this case is 1.5.
All right, so we're trying to figure out where is it if x1 is 0, where does x2 need to be so that we're exactly at the threshold? So that's going to be the x2 times the weight, which is a half, has to exactly equal the threshold, which is 3/4. So if we just solve that out, we get x2 equals 3/2. So okay, so that's this point here. That's going to be a dividing line. So anywhere above here, what is it going to return?
It will return, it'll break the threshold, and so it will return a 1.
So these are all going to be 1s, and then below this, these are all going to be 0s.
Right.
All right, well now we have a very, very skinny version of the picture. Well, what else can we do?
Well, we can do the same thing that we just did, except swap x2 and x1 because they have the same weights. So we could set x2 equal to 0 and figure out what value x1 has to be.
Good, and that seems like it would be exactly the same algebra. And so we get x1 is 3/2, gives us at the 1.5 point. Above here are going to be 1s, below here are going to be 0s. Okay, so now we've got two very narrow windows. But what we notice is that the relationships are all linear here. So this solving this linear inequality gives us a picture like this. So this perceptron computes a kind of half plane, right? So the plane that's above this line, the half plane that's above this line, is getting us the 1 answers, and below that line is giving us the 0 answers.
So Michael, can we generalize from this? So you're telling me then that because of the linear relationship drawn out by a perceptron, that perceptrons are always going to compute lines.
They're always going to compute, yeah, these half planes, right? So there's a dividing line where you're equal to the threshold, and that's always going to be a linear function, and then it's going to be, you know, to the right of it or the left of it or the above it or below it, but it's always going to be halvesies at that point.
Okay, so a perceptron's a linear function, and it computes hyperplanes.
Yeah, which maybe in some sense doesn't seem that interesting. But it turns out we're already in a position to compute something fascinating. So let's do a quiz. So this example that we created just at random actually is it computes an interesting function. So let's focus on just the case where our x1 is in the set 0, 1 and the x2 is in the set 0, 1. So those are the only inputs that we care about, combinations of those. What is y computing here? What is the name of that relationship, that function that's being computed? And so just as a hint, there's a nice short one-word answer to this if you can kind of plug it through and see what it is that it's computing. Charles, can you figure this out?
Yes, I believe I can. So the first thing to note is that because we're sticking with just 0 and 1 and not all possible values in between, we are thinking about a binary function. And the output is also binary, which makes me think of Boolean functions, where 0 represents false and 1 represents true, which is a common trick in machine learning.
All right, so and let me mark those on the picture here. So we're talking about the only 4 combinations are here. And you're saying in particular that we're interpreting these as combinations of true and false. So false, false, true, false, false, true, and true, true.
Exactly. And if you look at it, the only way that you get something above the line is when both are true. And that is called and.
And we'll also take conjunction. Right, exactly so. Exactly so. So this is, even though we're setting these numerical values, but it actually gives us a way of specifying a kind of logic gate.
Right. So here's a question for you, Michael. Could we do or?
That's a very good question. Or looks a lot like and in this space. It seems like it ought to be possible. So let's do that as a quiz. All right. So we're going to go in the opposite direction now, and we're saying we're going to tell you what we want y to be. We want y to be the or function. So it should be outputting a 1 if either x1 or x2 is 1, and otherwise it should output a 0. And what you need to do is fill in numbers for weight 1, weight 2, and theta so that it has that semantics. Now, just so you know, there is no unique answer here. There's a whole bunch of answers that will work, but we're going to check to see that you've actually typed in one that works. All right, Charles, let's figure this one out. It turns out, as I said, there's lots of different ways to make this work. But what we're going to do is move that line that we had for conjunction. What we really want to do now is figure out how to move it down so that now these 3 points are in the green zone. They're going to output 1 because they're the or. And the only one that's left in the 0 zone, in the red zone, is the 0, 0 case. So how are we going to be able to do that?
Well, since we want it to be the case that either x2 or x1 being 1 gets you above the line, then we need a threshold and a set of weights that put either one of them over. You don't have to have both of them. You only need one of them. So let's imagine a case where x1 is 1 and x2 is 0. Then basically, you're right. There's a whole lot of answers. So a weight of 1 for x1 would give you a 1, right?
Yes. Uh-huh.
And so if we made the threshold 1, that would work.
What about weight 2?
Well, we do exactly the same thing. So we set weight 2 equal to 1, and that means that in the case where both of them are 0, you get 0 plus 0, which gives you something less than 1. If one of them is 1 and the other is 0, you get 1, which gives you right at the threshold. And if both of them are 1, then you get 2, which is still greater than 1.
Good. All right. That seems like it works. The other way we could do it is we can keep the weights at, another way we can do it is keep the weights where they were before. That just moves this line nice and smoothly down. And then, right, so before we had a threshold of 1.5. Now we need a threshold of like a half ought to do it.
Yeah.
Or even less. As long as it's greater than 0. So a quarter should work as well. So good. So lots of different ways to do that. Right. And cool. Can we do not?
What's not of 2 variables?
That's a good question. Let's do not of 1 variable then.
Okay.
Maybe you should help me finish this picture here. So what we've got is x1 is our variable, and so it can take on any sort of values, and I marked -1, 0, and 1 here. And if we're doing not, right, then what should the output be for each of these different values of x1? So like if x1 is 0, then we want the output to be
1.
1. And if x1 is 1, we want the output to be
0.
0. All right, so now what we'd like you to do is say, okay, what should weight 1 be and what should theta be so that we get this kind of not behavior. All right, Charles, you were about to say how we can do this.
I think the answer is simply that we basically need to flip here's my thinking. We need to flip 0 and 1, which suggests that either our weight or our threshold needs to be negative. And since the threshold isn't above, it's going to end up being our weight being negative. So let's see. If we have a 0, we want to turn that into something above the threshold. And if it's a 1, we want it to be below the threshold. So why don't we make the weight -1?
Good.
And that will turn a 0 into a 0, and it'll turn a 1 into a -1.
All right.
And so then the threshold just has to be 0.
So that would mean that anything, I see. So anything that's negative will be greater than or 0 or negative will be greater than or equal to the threshold. And anything on the other side of that would be under the threshold. So we get this kind of dividing line at 1. So we're taking advantage of the fact that the equation had a greater than or equal to in it. So
right.
Yeah, right, that ought to be a not. So we've got and, or, and not are all expressible as perceptron units. So and, or, and not are all expressible as perceptron units.
Hey, that's great, because if we have and, or, and not, then we can represent any Boolean function.
Well, do we know that? We know that if we combine them together, we combine these perceptron units together, can we express any perceptron, or sorry, any Boolean function that we want using a single perceptron?
So what do we normally do in this case? So what's the most evil function we can think of?
Yes, indeed. Well, when we were working on decision trees, the thing that was so evil was the XOR, or parity more generally. So,
Right.
all right. I mean, maybe if we can do that, we can do anything. So let's give it a shot. All right. So here's what we're going to do. We're going to try to figure out how to compute XOR as, instead of a single perceptron, which we know is impossible, we can do it as a network of perceptron. And just to make it easier for you, here's how we're going to set it up. That we've got x1 and x2 as our inputs. We've got 2 units. This first unit is just going to compute an and we already know how to do that. We've already figured out what weights need to be here, and what the threshold needs to be so that the output will be the and of those 2 inputs. So that's all good. But what we don't know, what it turns out to be the case, that the second unit, with now 3 inputs, x1, x2, and the and of x1 and x2, can also be made to, or can be, now we can set the weights on that so that the output is going to be XOR. So what we'd like you to do is figure out how to do that. How do you set this weight that is the input of x1, this weight, which is the and input, and this weight, which is the x2 input, and the threshold, so that it's going to actually compute an XOR. And just so you know, this is not a trick question. You really can do it this time. So okay, so how are we going to solve this?
Okay, so I guess the first thing to do is, if you look at the table you have at the bottom, it tells us what the truth tables are for and XOR. Right? So we know that Boolean functions can all be represented as combinations of and, or, and not. So I'm going to recommend that you fill out that empty column you have with or.
All right, so or is like that.
Right, and you'll notice if you look at and, or, and XOR, that or looks just like XOR except at the very last row.
In the second, okay, good. And in that row.
Right, and on the other hand, tells us a 1 only on the last row. So what I'm going to suggest that we really want that last node to do in your drawing is to compute the or of x1 or x2 and produce the right answer, except in the case of the last row, which we only want to turn off when and happens to be true. So really what that node is computing or minus and.
All right, so how do we make this or minus and? So the way we did or before, well, we did it a couple different ways, but one is we gave weights of 1 on the 2 inputs and then a threshold of 1. And that made, ignoring everything else at the moment, this unit will now turn on if either x1 or x2 are on, and otherwise it'll stay off.
Right. So what's the worst case? The lowest value that you can get is when one of those is 1 and one of those is 0, which means that the sum into those will be, in fact, 1.
Yeah.
Right? So if the and comes out as being true, it's going to give us some positive value. So if we just simply have a negative weight there, that will subtract out exactly in the case when and is on. That's not going to quite give us the answer we want, but it's a good place to start to think about it.
All right, so like just a negative weight like -1?
Mm-hmm.
All right, so does that work?
Not quite.
All right, and why doesn't it work? Because certainly when and is off, then we really are just getting the or. That's all good. But if both x1 and x2 are both on, then the sum here is going to be 2 minus the 1 that we get from the and, which is still 1.
So -1 isn't enough.
-1, but maybe we can do more than that. Maybe we can do -2. What happens if we do -2? Then we've got x1 and x2, if they're both on, then we get a sum of 1 minus 2 plus 1, or 0, which is less than our threshold, so it will output 0. And in the other two cases, right, when and is off, then it just acts like or. So this actually kind of does the right thing. It's actually or minus kind of n times 2.
Right. And there you go. And of course, there's an infinite number of solutions to this.
All right, so in the examples up to this point, we've been setting the weights by hand to make various functions happen. And that's not really that useful in the context of machine learning. We'd really like a system that, given examples, finds weights that map the inputs to the outputs. And we're going to actually look at two different rules that have been developed for doing exactly that, figuring out what the weights ought to be from training examples. One is called the perceptron rule, and the other one's called gradient descent, or the delta rule. And the difference between them is the perceptron rule is going to make use of the thresholded outputs, and the other mechanism is going to use unthresholded values. All right, so what we need to talk about now is the perceptron rule, which is how to set the weights of a single unit so that it matches some training set. So we've got a training set, which is a bunch of examples of x. These are vectors. And we have y's, which are zeros and ones, which are the outputs that we want to hit. And what we want to do is set the weights so that we capture this same data set. And we're going to do that by modifying the weights over time.
Michael, what's the series of dashes over on the left?
Oh, sorry. Right. I should mention that. So one of the things that we're going to do here is we're going to give a learning rate for the weights W and not give a learning rule for the theta, but we do need to learn the theta. So there's a very convenient trick for actually learning them, and by just treating it as another kind of weight. So if you think about the way that the thresholding function works, we're taking a linear combination of the w's and the x's, and then we were comparing it to theta. But if you think about just subtracting theta from both sides, then in some sense theta just becomes another one of the weights, and we're just comparing to 0. So what I did here is I took the actual data, the x's, and I added what is sometimes called a bias unit to it. So basically, the input is 1 always to that, and the weight corresponding to it is going to correspond to negative theta ultimately. So just again, this just simplifies things so that the threshold can be treated the same as the weights. So from now on, we don't have to worry about the threshold. It just gets folded into the weights, and all our comparisons are going to be just to 0 instead of theta.
That's a neat trick.
Yeah. It certainly makes the math shorter. So okay, so this is what we're going to do. We're going to iterate over this training set, grabbing an x, which includes the bias piece, and the y, where y is our target, x is our input. And what we're going to do is we're going to change weight I, the weight corresponding to the ith unit, by the amount that we're changing the weight by. So this is sort of a tautology, right? This is really just saying the amount we change the weight by is exactly the delta W, in other words, the amount we change the weight by. So we need to define what that weight change is. The weight change is going to be defined as follows. We're going to take the target, the thing that we want the output to be, and compare it to what the network with the current weights actually spits out. So we compute this y hat, this approximate output y, by, again, summing up the inputs according to the weights, comparing it to 0. That gets us a 0, 1 value. And so we're now comparing that to what the actual value is. So what's going to happen here? If they're both zeros, so let's look at this. Each of y and y hat can only be 0 and 1. If they're both zeros, then this y minus y hat is 0. If they're both 1s, and what does that mean? It means that the output should have been 0, and the output of our current network really was 0. So that's kind of good. If they are both 1s, it means the output was supposed to be 1, and our network outputted 1, and the difference between them is going to be 0. But in this other case, y minus y hat, if the output was supposed to be 0, but we said 1, or network says 1, then we get a negative 1. If the output was supposed to be 1 and we said 0, then we get a positive 1. Okay, so those are the 4 cases for what's happening here. We're going to take that value, multiply it by the current input to that unit I, scale it down by this little thing that is going to be called the learning rate, and use that as the weight update change. So essentially what we're saying is if the output is already correct, either both on or both off, then there's going to be no change to the weights. But if our output is wrong, let's say that we are giving a 1 when we should have been giving a 0, that means the total here is too large. And so we need to make it smaller. How are we going to make it smaller? Whichever input, xi's, correspond to very large values, we're going to move those weights very far in a negative direction. We're taking this negative 1 times that value, times this little learning rate. All right, the other case is if the output was supposed to be 1, but we're outputting a 0, that means our total is too small. And what this rule says is increase the weights, essentially, to try to make the sum bigger. Now, we don't want to kind of overdo it, and that's what this learning rate is about. The learning rate basically says, well, figure out the direction we want to move things, and just take a little step in that direction. We're going to keep repeating over all of the input-output pairs, so we'll have a chance to get to really build things up. But we're going to do it a little bit at a time so that we don't overshoot. And that's the rule. It's actually extremely simple. Like actually writing this in code is quite trivial, and yet it does some remarkable things. So let's imagine for a second that we have a training set that looks like this. It's in 2 dimensions, just again so that it's easy to visualize. That we've got a bunch of positive examples, these green x's, and we've got a bunch of negative examples, these red x's, and we're trying to learn basically a half plane, right? We're trying to learn a half plane that separates the positive from the negative examples. So, Charles, do you see a half plane that we could put in here that would do the trick?
I do.
What would it look like?
It's that one.
By that one, do you mean this one?
Yeah, that's exactly what I was thinking, Michael.
That's awesome. Yeah, there actually isn't a whole lot of flexibility in what the right answer is in this case if we really want to get all the greens on one side and all the reds on the other. If there is such a half plane that separates the positive from the negative examples, then we say that the data set is linearly separable, right? That there is a way of separating the positive and negatives with a line. And what's cool about the perceptron rule is that if we have data that is linearly separable, the perceptron rule will find it. It only needs a finite number of iterations to find it. In fact, which I guess is really the same as saying that it will actually find it. It won't eventually get around to getting to something close to it. It will actually find a line, and it will stop saying, okay, I now have a set of weights that do the trick. So that's what happens if the data set is in fact linearly separable. And that's pretty cool. It's pretty amazing that it can do that. It's a very simple rule, and it just goes through and iterates and solves the problem. So Charles, do you see any and solves the problem? So
I can think of one. What if it's not linearly separable?
I see. So if the data is linearly separable, then the algorithm works. So the algorithm simply needs to only be run when the data is linearly separable. It's not generally that easy to tell, actually, when your data is linearly separable. Especially here we have it in 2 dimensions. If it's in 50 dimensions, knowing whether or not there's a setting of those parameters that makes it linearly separable, not so clear.
Well, there's one way you could do it.
What's that?
You could run this algorithm and see if it ever stops.
I see. Yes, of course there's a problem with that particular scheme, right? Which says, well, for one thing, this algorithm never stops. So wait, we need to address that. But really we should only be running this loop here while there's some error. So I neglected to say that before, but what you'll notice is if you continue to run this after the point where it's getting all the answers right, it's found a set of weights that linearly separate the positive and negative instances, what will happen is when it gets to this delta W line, that y minus y hat will always be 0. The weights will never change. We'll go back and update them by adding 0 to them repeatedly over and over and over again. So if it ever does reach 0 error, if it ever does separate the data set, then we can just put a little condition in there and tell it to stop the loop. So what you're suggesting is we could run this algorithm, and if it stops, then we know it's linearly separable. And if it doesn't stop, then we know that it's not linearly separable, right, by this guarantee.
Sure.
The problem is we don't know when finite is done, right? If this were like 1,000 iterations, we could run it for 1,000. If it wasn't done, it's not done. But all we know at this point is that it's a finite number of iterations. And so that could be 1,000, 10,000, a million, 10 million. We don't know. So we never know when to stop and declare the data set not linearly separable.
So if we could do that, then we would have solved the halting problem, and we'd all have Nobel Prizes.
Well, that's not necessarily the case, but certainly the other direction is true, that if we could solve the halting problem, then we could solve this. But it could be that this problem might be solvable even without solving the halting problem.
Fair enough. Okay.
So we're going to need a learning algorithm that is more robust to nonlinear separability or nonlinear non-separability. Does that sound right?
Nonlinear separability.
Nonlinear separability.
Non,
yeah, I think
left parenthesis, linear separability.
There
right
you go.
parenthesis.
That's right, negating the whole phrase. Very good. So, and gradient descent is going to give us an algorithm for doing exactly that. So what we're going to do now is think of things this way. So what we did before was we had a summation over all the different input features of the activation on that input feature times the weight, W, for that input feature. And we sum all those up and we get an activation. And then we have our estimated output as whether or not that activation is greater than or equal to 0. So let's imagine that the output is not thresholded when we're doing the training. And what we're going to do instead is try to figure out the weights so that the not thresholded value is as close to the target as we can. So this actually kind of brings us back to the regression story. We can define an error metric on the weight vector W. And the form of that's going to be 1/2 times the sum over all the data in the data set of what the target was supposed to be for that particular example, minus what the activation actually was, right? The activation being the dot product between the weights and the input. And we're going to square that. We're going to square that error, and we want to try to now minimize that.
Hey, Michael, can I ask you a question?
Sure.
Why 1/2 of that?
Yes. It turns out that in terms of minimizing the error, this is just a constant and it doesn't matter. So why do we stick in a half there? Let's get back to that.
Okay.
Just like in the regression case, we're going to fall back to calculus, right? Calculus is going to tell us how we can push around these weights to try to push this error down, right? So we would like to know, how does changing the weights change the error? And let's push the weights in the direction that causes the error to go down. So we're going to take the partial derivative of this error metric with respect to each of the individual weights so that we'll know for each weight which way we should push it a little bit to move in the direction of the gradient. So that's the partial so that's the partial derivative with respect to weight Wi of exactly this error measure. So to take this partial derivative, we just use the chain rule as we always do. And what is it to take the derivative of something like this? If you have this quantity here, we take the power, move it to the front, keep this thing, and then take the derivative of this thing. But so this now answers your question, Charles. Why do we put a half in there? Because down the line, it's going to be really convenient. The 2 and the half canceled out. So it's just going to mean that our partial derivative is going to look simpler, even though our error measure looked a little bit more complicated. So, so what we're left with then is exactly what I said, the sum over all these data points of what was inside this quantity here times the derivative of that. And here I expanded the A to be what the definition of the A. Now we need to take the partial derivative with respect to weight Wi of this sum that involves a bunch of the W's in it. So when we don't match the Wi, then that derivative is going to be 0 because changing the weight won't have any impact on it. The only place where changing this weight has any impact is at x sub I. So that's what we end up carrying down, that the summation disappears, and all that's left is just the one term that matches the weight that we care about. So this is what we're left with now. The derivative of the error with respect to any weight W sub I is exactly this sum, the sum of the difference between the activation and the target output times the activation on that input unit.
That looks exactly like, or almost exactly like, the rule that we used with perceptrons before.
It does indeed. What's the difference? Well, let's write this down. This is now just the derivative, but let's actually write down what our weight update is going to be, because we're going to take a little step in the direction of this derivative, and it's going to involve a learning rate. So here's our two update rules, what they end up being. The gradient descent rule that we just derived says that what we want to do is move the weights in the negative direction of the gradient. So if we negate that expression that we had before and take a little step in that direction, we get exactly this expression. Multiply the input on that weight times the target minus the activation. Whereas in the perceptron case, what we were doing is taking that same activation, thresholding it, like determining whether it's positive or negative, putting in a 0 or a 1, and putting that in here. That's what y hat is. So really, it's the same thing, except in one case we have done the thresholding, and in the other case we have not done the thresholding. But we end up with two different algorithms with two different behaviors. The perceptron has this nice guarantee of finite convergence, which is a really good thing, but that's only in the case where we have linear separability, whereas the gradient descent rule is good because, calculus. I guess that's not really an answer, is it? The gradient descent rule is good because it's more robust to data sets that are not linearly separable, but it's only going to converge in the limit to a local optimum. All right, is that the story there, Charles?
As far as I'm concerned.
So once we see these two things next to each other, it kind of raises the question, why don't we just use a gradient descent type approach on an error metric that's defined in terms of y hat instead of just the activation A? Because y hat is the thing that we really want to match the output. We don't really want the activation to match the output. There's no need for that. So it seems like there's a bunch of different possible reasons for that. It could be, well, we don't do that because it would just be computationally intractable. It's too much work. Another possibility would be, well, to do the gradient descent, you have to be able to take the derivative, and if we use it in this form, it's not differentiable, so we can't take the derivative. Another one is, well, sure, we can do all that. It's not intractable and it's not non-differentiable. It's differentiable. But if we do that, then the weights tend to grow too fast, and so you end up getting unstable answers. And then the last possible choice that we'll give you is you can do that, but you can get multiple different answers, and the different answers behave differently, and so this is really just to keep it from being ill-defined. So why don't we do gradient descent on y hat?
Well, there could be many reasons, but the main reason is it's not differentiable. It's a discontinuous function. There's no way to take a derivative at the point where it's discontinuous.
So this activation thing, the change from the activation to y hat has this big step function jump in it, right, at 0. So once the activation goes positive, actually at 0, it jumps up to 1, and before that it's not. So the derivative is basically 0, and then not differentiable, and then 0 again. So really the 0 is not giving us any direction to push in terms of how to fix the weights. And the undefined part, of course, doesn't really give us any information either. So this algorithm doesn't really work if you try to take the derivative through this discontinuous function. But it does kind of, what if we made this more differentiable? Like, what is it that makes this so undifferentiable? It's this really pointy spot, right? So you could imagine a function that was kind of like this, but then instead of the pointy spot, it kind of smoothed out a bit, like that. So kind of a softer version of a threshold, which isn't exactly a threshold, but at least it's differentiable. So that would kind of force the algorithm to put its money where its mouth is. Like, if that really is the reason that the problem is non-differentiable, fine, we'll make it differentiable. Now how do you like it? I don't know. How do we like it now?
Well, I'll tell you how much I like it when you show me a function that acts like that.
Challenge accepted. We're going to look at a function called the sigmoid. Sigmoid meaning S-like, right? Sigma-ish, sigmoid. So we're going to define the sigmoid using the letter sigma, and it's going to be applied to the activation just like we were doing before. But instead of thresholding it at 0, what it's instead going to do is compute this function of a, 1 over 1 plus e to the minus a. And what do we know about this function? Well, ought to be clear that as the activation gets less and less and less, we'd want it to go to 0, and in fact it does, right? So as a goes to negative infinity, the negative a goes to infinity. E to the infinity is something really, really big. So it's 1 over 1 plus something really big, which is like 1 over something huge, which is almost 0. So the sigmoid function goes toward this function that we defined here, goes to 0 as the activation goes to negative infinity. That's great. That's just like the threshold. And as the activation gets really, really large, we're talking about e to the minus something really large, which is like e to the almost, or like e to the negative infinity, which is like almost 0. So 1 over 1 plus 0 is essentially 1. So on the one limit, it goes towards 0, and the other limit, it goes towards 1. And in fact, we can just draw this so you can see what it really looks like. Minus 5 and below, it's essentially at 0, and then it makes this kind of gradual. You can see why it's sigmoid, right? It's an S-shaped curve. Then it comes back up to the top, and it's basically at 1 by the time we get to 5. So instead of just an abrupt transition at 0, we have this gradual transition between negative 5 and 5. And this is great because it's differentiable. So what do you think, Charles? Does this answer your question?
It does. I buy that.
All right, good. So if we have units like this, now we can take derivatives, which means we can use this gradient descent idea all over the place. So not only is this function differentiable, but the derivative itself has a very beautiful form. In particular, it turns out that if you take the derivative of this sigma function, it can be written as the function itself times 1 minus the function itself. So this is just really elegant and simple. So if you have the sigma function in your code, there's nothing special that you need for the derivative. You can just compute it this way. So we would it's not a bad exercise to go through and do this and practice your calculus. We just we just did this together. But it's not that fun to watch, so I would suggest doing it on your own. And if you have any trouble, we'll provide additional information for you to help you work that out.
But when you do it on your own, make certain no one's watching.
Well, they can watch. They just probably won't enjoy it very much. So can we say anything about why this form kind of makes sense? So what's neat about this is as our activation gets very, very negative, then our sigma value gets closer and closer to 0. And if you look at what our derivative is there, it's something like 0 times something like 1 minus 0. Whereas the derivative, as you get to very, very large a's, that's like sigma is going to 1, and you get 1 times 1 minus 1, so essentially 1 times 0. So you can see the derivatives flatten out for very large and very negative a's. And when a is like 0, so what happens when a is like 0? Boy, what does happen when a is like 0? Charles, what happens if we plug 0 into this sigma function?
You get 1/2.
Is that obvious? Oh, I see. Because e to the minus a, that's 0. So e to the 0 is 1. 1 over 1 plus 1, so 1/2. And then our derivative at that point is 1/2 times 1/2, or a quarter. So that's kind of neat.
Mm-hmm.
So this is really, it's in a very nice form for being able to work with it.
But it's probably worth saying that surely you could use other functions that are differentiable, and there might be good reasons to do that. This one just happens to be a very nice way of dealing with the thresholding question.
Yeah, and there's other ways that are also nice. So again, the main properties here are that as activation gets very negative, it goes to 0. As activation gets very positive, it goes to 1. And there's this smooth transition in between, and there's other ways of making that shape. All right, so we're now in a great position to talk about what the network part of the neural network is about. So now the idea is that we can construct, using exactly these kinds of sigmoid units, a chain of relationships between the input layer, which are the different components of x, with the output, y. And the way this is going to happen is there's other layers of units in between that each one is computing the weighted sum, sigmoided, of the layer before it. These other layers of units are often referred to as hidden layers because you can kind of see the inputs and you can see the outputs. This other stuff is less constrained or indirectly constrained. And what's happening is that each of these units, it's running exactly that kind of, take the weights, multiply by the things coming into it, put it through the sigmoid, and that's your activation. That's your output. So what's cool about this is in the case where all these are sigmoid units, this mapping from input to output is differentiable in terms of the weights. And by saying the whole thing is differentiable, what I'm saying is that we can figure out for any given weight in the network how moving it up or down a little bit is going to change the mapping from inputs to outputs. So we can move all those weights in the direction of producing something more like the output that we want, even though there's all these sort of crazy nonlinearities in between. And so this leads to an idea called backpropagation, which is really just at its heart a computationally beneficial organization of the chain rule. We're just computing the derivatives with respect to all the different weights in the network, all in one convenient way that has this lovely interpretation of having information flowing from the inputs to the outputs and then error information flowing back from the outputs towards the inputs. And that tells you how to compute all the derivatives and then therefore how to make all the weight updates to make the network produce something more like what you wanted it to produce. So this is where learning is actually taking place. And it's really neat. This backpropagation is referring to the fact that the errors are flowing backward. Sometimes it's even called error backpropagation.
Nice. So here's a question for you, Michael. What happens if I replace the sigmoid units with some other function? And let's say that function is also differentiable.
Well, if it's differentiable, then we can still do this basic kind of trick that says we can compute derivatives, and therefore we can move weights around to try to get the network to produce what we want it to produce.
That's a big win. Does it still act like a perceptron?
Well, even this doesn't act exactly like a perceptron, right? So it's really just analogous to a perceptron because we're not really doing the hard thresholding. We don't have guarantees of convergence in finite time. In fact, the error function can have many local optima. And what we mean by that is this idea that we're trying to set the weight so that the error is low, but you can get to these situations where none of the weights can really change without making the error worse. And you'd like to think, well, good, then we're done. We've made the error as low as we can make it. But in fact, it could actually just be stuck in a local optimum, that there's a much better way of setting the weights. It's just we have to change more than just one weight at a time to get there.
Oh, so that makes sense. So if we think about the sigmoid, the sigmoid and the error function that we picked, right? The error function was sum of squared errors. So that looks like a parabola in some high dimensional space. But once we start combining them with others like this over and over and over again, then we have an error space where there might be lots of places that look low, but only look low if you're standing there, but globally would not be the lowest point.
Right, exactly right. And so you can get these situations in just the 1-unit version where the error function, as you said, is this nice little parabola, and you can move down the gradient, and when you get down to the bottom, you're done. But now when we start throwing these networks of units together, we can get an error surface that just in its cartoon form looks crazy like this, that it's smooth, but there's these places where it goes down, it comes up again, goes down maybe further, comes up again, doesn't come down as far, and you could easily get yourself stuck at a point like this where you're not at the global minimum, you're at some local optimum. So one of the things that goes wrong when you try to actually run gradient descent on a complex network with a lot of data is that you can get stuck in these local minima. And then you start to wonder, boy, is there some other way that I can optimize these weights? I'm trying to find a set of weights for the neural network that tries to minimize error on the training set. And so gradient descent is one way to do it, and it can get stuck. But there's other kinds of advanced optimization methods that become very appropriate here. And in fact, there's a lot of people in machine learning who think of optimization and learning as kind of being the same thing, that what you're really trying to do in any kind of learning problem is solve this high order, very difficult optimization problem to figure out what the learned representation needs to be. So I just want to mention in passing various kinds of advanced methods that people have brought to bear. There's things like using momentum terms in the gradient, which basically where the idea in momentum is as we're doing gradient descent, so imagine this is our error surface, we don't want to get stuck in this little bowl here. We want to kind of pass all the way through it to get to this bowl. So maybe we need to just, continue in the direction we've been going. So instead of, think of it as a kind of a physical analogy. Instead of just going to the bottom of this hill and getting stuck, it can kind of bounce out and pop over and come to what might be a lower minima later. There's a lot of work in using higher order derivatives to better optimize things instead of just thinking about the way that individual weights change the error function to look at combinations of weights, Hamiltonians and whatnot. There's various ideas from randomized optimization, which we're going to get to in a sister course that can be applied to make things more robust. And sometimes it's worth thinking, you know what, we don't really want to just minimize the error on the training set. We may actually want to have some kind of penalty for using a structure that's too complex. I mean, when did we see something like this before, Charles?
When we were doing regression, and we were talking about overfitting.
What's a more or less complex network?
Well, there's two things you can do with networks. You can add more and more nodes, and you can add more and more layers.
Good. So if the more nodes that we put into a network, the more complicated the mapping becomes from input to output, the more local minima we get, the more we have the ability to actually model the noise, which brings up exactly the same overfitting issues. It turns out there's another one that's actually really interesting in the neural net setting, which I think didn't occur to people in the early days, but it became clearer and clearer over time, which is that you can also have a complex network just because the numbers, the weights, are very large. So same number of weights, same number of nodes, same number of layers, but larger numbers often leads to a more complex network and the possibility of overfitting. And so sometimes we want to penalize a network not just by giving it fewer nodes or layers, but also by keeping the numbers in a reasonable range. Does that make sense?
Makes perfect sense.
So this brings up the issue of what neural nets are more or less appropriate for. What is the restriction bias and the inductive bias of this class of classifiers and regression algorithms? So, Charles, can you remind us what restriction bias is?
Well, restriction bias tells you something about the representational power of whatever data structure it is that you're using. So in this case, the network of neurons. And it tells you the set of hypotheses that you're willing to consider.
Right. So if there's a great deal of restriction, then there's lots and lots of different kinds of models that we're just not even considering. We're restricting our view to just a subset of those. So in the case of neural nets, what restrictions are we putting?
Well, and we started out with a simple perceptron unit, and that we decided was linear. So we were only considering planes. Then we moved to networks so that we could do things like XOR, and that allowed us to do more. And then we started sticking sigmoids and other arbitrary functions into nodes so that we could represent more and more. And you mentioned that if we let the weights get big and we have lots of layers and lots of nodes, we can be really, really complex. So it seems to me that we're actually not doing much of a restriction at all. So let me ask you this then, Michael. What kind of functions can we represent? Clearly we can represent Boolean functions because we did that. Can we represent continuous functions?
That's a great question to ask. We should try to figure that out. So in the case, as you said, in Boolean functions, we can, if we give ourselves a complex enough network with enough units, we can basically map all the different subcomponents of any Boolean expression to threshold-like units and basically build a circuit that can compute whatever Boolean function we want. So that one definitely can happen. So what about continuous functions? So what is a continuous function? A continuous function is one where as the input changes, the output changes somewhat smoothly, right? There's no jumps in the function like that.
Well, there's no discontinuities, that's for sure.
All right, now if we've got a continuous function that we're trying to model with a neural network, as long as it's connected, it has no discontinuous jumps in any place in the space, we can do this with just a single hidden layer as long as we have enough hidden units, as long as there's enough units in that layer. And essentially one way to think about that is if we have enough hidden units, each hidden unit can worry about one little patch of the function that it needs to model. And the patches get set at the hidden layer, and at the output layer they get stitched together. And if you just have that one layer, you can make any function as long as it's continuous. If it's arbitrary, we can still represent that with a neural network. Any mapping from inputs to outputs we can represent, even if it's discontinuous, by just adding one more hidden layer, so 2 total hidden layers. And that gives us the ability to not just stitch together these patches at their seams, but also to have big jumps between the patches. So, in fact, neural networks are not very restrictive in terms of their bias as long as you have a sufficiently complex network structure, right? So maybe multiple hidden layers and multiple units.
So that worries me a little bit, Michael, because it means that we're almost certainly going to overfit, right? If we can have arbitrarily complicated neural networks, then we can represent anything we want to, including all of the noise that's represented in our training set. So how are we going to avoid doing that?
Excellent question. So it seems like there isn't exactly that worry. But it is the case, though, that when we train neural networks, we typically give them some bounded number of hidden units, and we give them some bounded number of layers. And so it's not like any fixed network can actually capture any arbitrary function. So any fixed network can only capture whatever it can capture, which is a smaller set. So going to neural nets in general doesn't have much restriction, but any given network architecture actually does have a bit more restriction. So that's one thing. The other is, hey, well, we can do with overfitting what we've done the other times when to deal with overfitting, and that's to use ideas like cross-validation. And we can use cross-validation to decide how many hidden layers to use. We can use it to decide how many nodes to put in each layer, and we can also use it to decide when to stop training because the weights have gotten too large. So, and it's probably worth pointing this out, that this is kind of a different property from the other classes of supervised learning algorithms we've looked at so far. So in a decision tree, you build up the decision tree, and you may have overfit, but it is what it is. In regression, you solve the regression problem, and again, that may have overfit. What's interesting about neural network training is it's this iterative process that you started out running, and as it's running, it's actually errors going down and down and down. So in this standard kind of graph, we get the error on the training set dropping as we increase iterations. It's doing a better and better job of modeling the training data. But in classic style, if you look at the error in some kind of held out test set or maybe in a cross-validation set, you see the error starting out kind of high and maybe dropping along with this. And then at some point, it actually turns around and goes the other way. So here, even though we're not changing the network structure itself, we're just continuing to improve our fit, we actually get this pattern that we've seen before, that the cross-validation error can turn around, and at this at this low point, you may want to just stop training your network there. The more you train it, possibly the worse you'll do. And again, it's reflecting this idea that the complexity of the network is not just in the nodes and the layers, but also in the magnitude of the weights. Typically what happens at this turnaround point is some weights are actually getting larger and larger and larger. So I just wanted to highlight that difference between neural net function approximation and what we see with some of the other algorithms. All right, another issue that we want to make sure that we think about each time we introduce a new kind of supervised learning representation is to ask what its preference bias is. So Charles, can you remind us what preference bias is?
Like restriction bias tells you what it is you are able to represent. Preference bias tells you something about the algorithm that you're using to learn that tells you, given two representations, why it would prefer one over the other. So perhaps if we think back what we talked about with decision trees, we preferred trees where nodes near the top had high information gain. We preferred correct trees. We preferred trees that were shorter to ones that were longer unnecessarily, and so on and so forth. So that actually brings up a point here, which is we haven't actually chosen an algorithm. You talked about how derivatives work, how backpropagation works, but you missed telling me one very important thing, which is how do we start? You tell me how to update the weights, but how do I start out with the weights? Do they all start out at 0? Do they all start out at 1? How do you usually set the weights in the beginning?
Yes, indeed. We did not talk about that. It's really important. You can't run this algorithm without initializing the weights to something, right? We did talk about how you update the weights, but they don't just, start undefined, and you can't just update something that's undefined. So we have to set the initial weights to something. So a pretty typical thing for people to do is small random values. So why do you suppose we want random values?
Because we have no particular reason to pick one set of values over another. So we start somewhere in the space. Probably helps us to avoid local minima.
Yeah, kind of. I mean, there's also the issue of, well, if we run the algorithm multiple times, if it gets stuck, we'd like it to not get stuck exactly there again if we run it again. So it gives some variability, which is a helpful thing in avoiding local minima. And why do you suppose it's important to start with small values?
Well, you just said in our discussion before that if the weights get really big, that can sometimes lead to overfitting because it lets you represent arbitrarily complex functions.
Good. And what does that tell us about what the preference bias is then?
Well, if we start out with small random values, that means we're starting out with low complexity. So that means that we prefer simpler explanations to more complex explanations. And of course, the usual stuff like we prefer correct answers to incorrect answers and so on and so forth.
So you'd say that neural nets implement, or maybe we should say that neural networks implement a kind of bias that says prefer correct over incorrect, but all things being equal, the simpler explanation is preferred.
Well, if you have the right algorithm, if the algorithm starts with small random values and tries to stop, and when you start overfitting, then yeah, because you're going to start out with the simpler explanations first before you allow your weights to grow. So yeah, I buy that.
So this is reminiscent of a principle that's known as Occam's razor, which is often stated as entities should not be multiplied unnecessarily. And given that we're working with neural networks, there's a lot of unnecessary multiplication that happens. But in fact, this actually is referring to exactly what we've been talking about. So this unnecessarily is one interpretation of this is that, well, when is it necessary? It's necessary if you're getting better explanatory power. You're fitting your data better. So unnecessarily would mean, well, we're not doing any better at fitting the data. If we're not doing any better at fitting the data, then we should not multiply entities. And multiplied here means make more complex. So don't make something more complex unless you're getting better error. Or if two things have similar error, choose the simpler one. Use the one that's less complex. That has been shown to, if you mathematize this and you use it in the context of supervised learning, that we're going to get better generalization error with simpler hypotheses. So that brings us to the end of the topics that we're going to talk about in terms of neural nets. There's going to be some interesting stuff for you to do in terms of the homeworks, where you'll be exposed to some other important concepts. But that's all we're going to lecture about for now. So let's just remind ourselves what exactly we covered in the neural net section. So Charles, what do you remember?
I remember perceptrons. I remember.
And a perceptron was a threshold unit, a linear threshold unit. And we could put networks of them together.
Yes.
To produce any Boolean function. What else? Oh, we had a learning rule for perceptrons, which runs in finite time for linearly separable data sets.
And we learned a general differentiable rule. And in general, we learned about backpropagation using gradient descent.
And we talked a little bit about the preference and restriction biases of neural networks. All right, till next time.
See you, Michael.